Welcome to the deep dive. I am so glad you're joining us today because we are looking at something that is actively rewriting the rules of how you work with technology.
It really is a fundamental shift.
Yeah, because, you're likely already very familiar with large language models. You know the standard workflow. You write a prompt, you send it off, and you wait for a static answer.
Right, it's a brilliant autocomplete.
Exactly. But it's fundamentally a passive transaction. And that paradigm is shifting.
Rapidly.
We're moving away from an AI that just answers your prompt toward an AI that actually plans out a multi-step solution.
One that searches the live web to fill in its own knowledge dumps.
Right. Or even writes custom code to build tools from scratch when it gets stuck.
And then spins up a collaborative team of specialized AI experts to debate and solve your problem.
Which, it sounds futuristic, right?
It does, but this is the exact engineering reality we're transitioning into right now. The industry refers to this shift as moving from passive generation to agentic reasoning.
Agentic reasoning. Okay, and to map out exactly how this transforms the software you use every day, we're pulling from a massive, really groundbreaking stack of sources today.
Yeah, specifically a comprehensive roadmap paper.
Right, it's titled Agentic Reasoning for Large Language Models. And this wasn't just put together by one lab. This was compiled by top researchers across the board. We're talking UIUC, Meta, Amazon, Google DeepMind, UCSD, and Yale.
It's a real who's who of the AI research world.
It is. So our mission for this deep dive is to unpack this massive shift from static models to active, self-improving agents and figure out what it actually means for your day-to-day workflow.
And to really grasp the magnitude of this shift, we have to reframe how we think about a language model's core function.
How so?
While traditional LLM reasoning is inherently closed world.
Okay.
It's a single-pass system. It relies entirely on the parameters it was trained on to just, predict the next word in a sequence.
So it's locked in a box.
Exactly. It doesn't truly interact with the outside world, it's constrained by its context window, and it certainly doesn't adapt its strategy mid-task.
Right.
Agentic reasoning changes the architecture entirely. We are reframing these models as autonomous agents operating within a dynamic think-act loop.
A think-act loop.
Yes. They plan their moves, they manipulate external environments, they wield software tools, and crucially, they adapt based on the feedback they receive.
Right. It's basically the difference between asking someone to recite a textbook from memory and asking someone to go to a laboratory, run a series of novel experiments, analyze the data, and write a completely new research paper.
That's a great analogy. It requires a totally different architecture.
Okay, let's unpack this, because to understand how we get to these massive AI teams autonomously solving complex problems, we actually have to zoom all the way in on a single agent first.
We do.
How does an AI actually bridge that gap between generating text, which is, what it was originally built to do, and taking meaningful action in a complex digital world?
That bridge is built on a very specific control theoretic framework.
Okay.
The sources look at this through the lens of what is called a partially observable Markov decision process.
That is a mouthful.
It is. A POMDP, for short.
A POMDP.
Okay.
A partially observable Markov decision process. That implies the AI is operating in an environment where it simply doesn't have all the information up front, right?
Precisely.
So think of it like playing poker instead of chess.
Oh, I like that.
Yeah, because in chess, you can see every piece on the board. You have perfect information. But in poker, you only know your own hand, and you have to infer the rest of the game state before making a bet.
That is a highly accurate way to look at it because the environment is partially hidden or, constantly changing. The AI cannot just act blindly.
Right.
In traditional text generation, the model observes your prompt and acts by outputting text. One step.
Done.
Right. But under a POMDP framework for agentic reasoning, the model's policy is split.
Split.
The AI actually has to perform internal computation in what they call a latent reasoning space before it commits to an external action.
So it's forced to generate a reasoning trace like an internal thought process before it touches an external API or a database.
Precisely. And this internal reasoning space is what unlocks the first core capability of these agents, which is planning.
I think planning.
Yes, because the agent is thinking before acting, it can take a massive ambiguous goal and decompose it into a sequence of manageable, verifiable subtasks.
Which is critical because if I ask an agent to, say, build a scalable e-commerce backend, I don't want it to just start vomiting Python code.
No, that would be a disaster.
Right. It needs to map out the database schema, then set up the authentication, and then write the routing logic.
Yeah.
How does it actually look ahead to do that?
It uses sophisticated search algorithms. The researchers detail techniques where agents simulate tree traversal algorithms.
Like what?
Things like Monte Carlo tree search or MCTS and A-star search.
Okay, for those who might not be deep into computer science algorithms, Monte Carlo tree search is essentially a way of simulating multiple different futures, right?
Exactly. The AI constructs a decision tree. It says, if I take action A, it leads to these possible states. If I take action B, it leads to these.
It's playing out the scenarios.
It simulates those paths forward, scores the likelihood of success for each branch, and verifies the logic before it takes an action in the real world that cannot be easily undone.
That's incredible.
And the sources also highlight that agents formalize these plans using structured code-like artifacts.
Like what kind of artifacts?
Specifically PDDL, which stands for Planning Domain Definition Language.
PDDL, so that's basically a blueprint language.
Exactly.
It allows the AI to map out the exact prerequisites needed before starting a task. It ensures the AI knows it has to buy the lumber before it tries to build a house.
That structuring of logic is what provides actual foresight, but foresight is only useful if you have the means to execute the plan.
Right.
Which brings us to the second core capability, tool use.
Tool use.
Yeah.
Because an LLM trying to execute complex mathematics or pull real-time stock data using only its internal weights is, well, it's highly inefficient.
It's prone to error.
Yeah, it's like trying to calculate a massive algorithmic equation in your head.
Yeah.
You might get close based on intuition, but it's much safer to just reach out and pick up a calculator.
And that realization, knowing when to pick up the calculator, is governed by frameworks like REACT.
React.
Yes, which stands for reasoning plus acting. Under the REACT paradigm, agents interleave their internal thoughts with external actions.
So they go back and forth.
Right. The agent thinks, I need to calculate the standard deviation of this data set, but I am a language model prone to arithmetic errors. I should write a Python script to calculate this accurately. So it invokes a code execution tool, runs the script, reads the output back into its context, and then continues reasoning.
And what's really striking in the source material is the sheer scale of this tool use. We aren't just talking about hooking an LLM up to a calculator and a calendar app.
No, not at all.
The researchers point to orchestration frameworks like Hugging GPT or Task Matrix. These systems act as a bridge between the foundation model and literally millions of distinct specialized APIs.
They manage incredibly complex dependencies. An agent using Task Matrix can decide to call a vision model to analyze an image, take the JSON output from that vision model, format it, and feed it directly into a totally different tool to generate an audio description.
Wow.
It's dynamically routing information across a vast ecosystem of software.
So it's effectively orchestrating a symphony of external software.
Yeah.
But that reliance on external information brings up a massive pain point that everyone using AI deals with, which is hallucinated or outdated information.
Yes, the knowledge cutoff problem.
Right. If an AI needs a fact from 2025, but its training data cuts off in 2023, it fails. I know a lot of developers use traditional RAG retrieval augmented generation to solve this by hooking the model up to a database. But the sources draw a really hard line between traditional RAG and true agentic search.
They do, because traditional RAG is fundamentally a static process. It's a one-shot query.
You ask a question, and the system retrieves a few documents that match your keywords.
Exactly. It stuffs them into the prompt, and the AI generates an answer based on whatever it was handed.
And if the retrieved documents are irrelevant or miss the nuance of the question,
the AI just hallucinates or fails. Agentic search, on the other hand, is dynamic. Systems like Self-Ask or Agent G autonomously control the search process. They decide when they need more context.
they act as their own researchers.
Yes.
If the first search returns confusing or contradictory results, they don't just blindly summarize it. They pause, refine their search parameters, and query the database again mid-task.
Furthermore, they can navigate heterogeneous data sources. An agentic search system can choose to read an unstructured web page to get a general overview, and then decide to query a highly structured knowledge graph to trace the specific relationships between two corporate entities.
So it's an active, multi-step investigation rather than a passive retrieval. Now, before we move past this foundational level, there is a technical distinction that the researchers emphasize about how these capabilities are actually embedded into the AI. They categorize it into two optimization modes.
Right. in-context reasoning, and post-training reasoning.
Let's break those down.
This is crucial for understanding how the models actually operate. In-context reasoning relies entirely on prompt design and orchestration at inference time.
Meaning while the model is actually running.
Yes. The model's underlying weights, its core neural network, do not change. You are simply giving it a highly structured environment and scaling the compute during the interaction to give it room to plan and call tools.
So you're basically giving a standard model a very strict set of instructions and a scratch pad to work on.
Correct. But post-training reasoning is entirely different. This is where you internalize these agentic skills directly into the model's parameters.
They're baking it in.
Exactly. Through techniques like reinforcement learning or supervised fine-tuning, you fundamentally alter the model so that agentic behavior is its native state.
Okay, that makes sense.
The text highlights Toolformer as a prime example of this. It's a model explicitly trained to predict and generate its own API calls organically without needing a complex orchestration layer wrapped around it. Both of these modes are actively driving the field forward.
But here's where it gets really interesting, and we have to pivot conceptually here. An agent that can plan, write code, and dynamically search the web is incredibly powerful.
Absolutely.
But what happens when that agent executes an API call and it fails? Or when it writes a piece of code that throws a syntax error?
That's the real test.
Exactly. This moves us from agents that just act to agents that self-evolve. We were talking about a meta-learning loop where agents get better on their own through cumulative experience.
This represents a profound shift away from human-dependent training. We're looking at agents mimicking human trial and error, but executing it without human supervision.
The researchers break down this self-evolution into 3 distinct feedback regimes, right?
Yes. The first is reflective feedback. This occurs dynamically during inference. A prominent example is the reflection framework.
Reflection with an X.
Yes. Here, the AI acts as its own internal critic. It generates a draft output, analyzes it for logical inconsistencies or missing steps, and then revises its own work before presenting a final solution.
But wait, doesn't running a loop of trial and error at computer speed risk rapid hallucination? I mean, if the AI is just guessing and critiquing itself millions of times without a grounding mechanism, couldn't it confidently spiral in completely the wrong direction?
That is exactly why the second regime, validator-driven feedback, is so vital. It provides a hard guardrail.
Okay, how does that work?
Validator-driven feedback doesn't rely on the AI's internal critique. It relies on deterministic signals from the environment. The paper extensively discusses SW Bench,
The software engineering evaluation framework.
Yes. In this environment, an agent writes a piece of code to fix a bug, and then it literally runs a unit test.
Right, so the AI isn't introspecting about whether the code is good. It just looks at the binary pass or fail signal from the compiler.
Exactly. If the unit test fails, the agent reads the error traceback, discards the flawed logic, adjusts its approach, and tries again.
That's brilliant.
It is interacting with the environment purely based on external ground truth validation. It cannot spiral into a hallucination because the compiler will simply reject the code until it actually works.
And the third regime is parametric adaptation, which takes these lessons and bakes them into the model permanently.
Correct.
Instead of just revising a draft in the current context window, the model updates its actual weights based on the feedback. It remembers the lesson for the next user.
But for an agent to truly evolve over long periods of time, it needs to be able to recall those lessons efficiently, which brings up the evolution of agentic memory.
Right, because when most people think of AI memory, they just think of a chat transcript, like scrolling up to see what was said 10 minutes ago.
And for complex, long-horizon tasks, that passive, flat memory structure is completely inadequate. You cannot build a lifelong, persistent agent on a chronological text transcript.
The context window gets bloated.
Exactly, and retrieving specific insights becomes mathematically inefficient. The sources detail a major shift towards structured memory.
Like GraphRag or the Memenzu system.
Yes. Instead of storing sentences, these systems extract entities, attributes, and their semantic relationships and map them out into dynamic knowledge graphs.
Okay, so give me an example of how that works in practice.
If the agent learns a specific fact about a user's coding preferences in week 1 and learns a related fact about their database architecture in week 3, it connects those two nodes in its memory graph.
I see.
When queried later, it isn't just searching for keywords. It is traversing a relationship map to draw synthesized conclusions.
It's basically building and maintaining its own internal Wikipedia.
That's a good way to put it.
But functionally, it's doing this by continuously refining how data points interact. And there's a specific mechanism mentioned regarding memory that is fascinating. Post-training memory control. The AI is actively managing its own storage capacity.
This addresses a fundamental computing constraint. An agent cannot store every single interaction forever without suffering massive latency and efficiency drops.
It would just bog down.
Right. So the researchers point to systems like MemAgent or Memory R1. These architectures use reinforcement learning to literally teach the AI how to autonomously manage its own memory state.
So the AI is being treated as a manager of its own brain space.
Exactly.
It receives a positive reward signal for retaining information that proves useful in solving later problems, and it's actively rewarded for deleting irrelevant or redundant data to maintain efficiency.
It's learning to prioritize information based on utility, and that autonomous management leads directly into what might be the most significant technical leap discussed in the sources.
The aha moment.
Yes. We have established that agents use tools and that they learn from their mistakes. But what happens if a self-evolving agent maps out a complex plan, searches its entire available tool library, and realizes the specific tool it needs to accomplish the task simply does not exist?
In a traditional system, it would just hit a wall, right? It would output an error message and wait for a human developer to build the tool.
Yes, but the sources outline a framework called LATM large language models as tool makers.
When faced with a missing capability, a powerful agent transitions into a tool maker.
It writes custom Python code or scripts to build a tailored tool from scratch on the fly.
Wow.
It then tests that newly minted tool against the environment to ensure it functions correctly. Once verified, it passes this new tool down to a lighter, more efficient tool user agent to execute the actual task.
That is a fundamental expansion of the AI's action space.
Mm.
You assign a goal, the AI realizes it lacks the software to achieve the goal, so it engineers the necessary software, tests it, and then completes your goal. The system is literally bootstrapping its own capabilities.
It removes the human bottleneck in software development for edge case problems,
Yeah.
but it also highlights a limitation.
What's that?
One self-evolving agent, even one capable of building its own tools, is still bound by the compute limitations and latent reasoning capacity of a single model.
Which brings us to the final evolution discussed in the roadmap. Collective intelligence and the rise of the multi-agent system, or MAS.
Right.
Because if a task is too scrawling like writing the entire architecture for a new video game or synthesizing decades of pharmaceutical research to propose a new drug, a single agent is going to bottleneck.
And the critical insight here is that we aren't scaling intelligence simply by throwing more compute at a single massive model. We're doing it by forcing models to defend their logic against peer review from other models.
A multi-agent system relies on a strict role taxonomy. It is an ecosystem of specialized digital entities.
It's not just a bunch of clones shouting at each other.
Right. It's essentially an automated corporate team.
Yeah.
And anyone who has spent time in a corporate Slack channel knows you can't just put 10 software engineers in a chat room and expect a cohesive product without a management structure.
Exactly. The sources map out these roles very clearly. At the apex of this taxonomy is the leader or coordinator agent, the boss. This agent rarely executes the ground-level work. Its function is to maintain global coherence. It receives the massive overarching prompt, breaks it down into actionable sub-goals, and assigns them to the appropriate specialized agents. Most importantly, the leader acts as the arbitrator.
Because if you have multiple models working on a complex problem, they're going to produce contradictory outputs.
Right.
I mean, I've seen human projects stall for weeks because the front-end team and the back-end team fundamentally disagree on an implementation.
It happens all the time.
So how does an AI leader arbitrate that?
It requires the other agents to provide their reasoning traces. The leader analyzes the logic of the conflicting approaches and dictates the path forward to keep the system from deadlocking.
Okay, and who is doing the actual work?
Below the leader, you have planners who sequence the dependencies and workers who execute the specific tasks. They write the code, run the searches, or parse the data.
But the most interesting roles are the verifiers and the critics.
Oh, absolutely.
Their entire existence is dedicated to adversarial review. They take the output from the workers and aggressively try to poke holes in it, searching for edge cases, bugs, or logical fallacies before the leader accepts the work.
This adversarial setup leverages the AI's natural capacity for debate and refinement. But the true technical marvel here is the nature of their communication.
Oh, so
They are not exchanging raw binary data or structured API calls in the way traditional microservices do.
the communication itself is an extension of the reasoning process.
Exactly. When these agents collaborate, one agent's external action, its final output, or its critique, acts as a natural language prompt that triggers the internal reasoning chain of the next agent.
That's wild.
They share interconnected memory spaces, and they resolve their complex disagreements through multi-turn natural language interactions. You have an ecosystem of different agents, often powered by entirely different underlying models from different companies, co-evolving their solutions and aligning their outputs to achieve a unified massive goal.
So what does this all mean? We have covered immense technical ground today, from the foundation of the Think-Act Loop and PUMDP frameworks to agents that build their own memory graphs and write their own tools, all the way to massive debating teams of specialized AI. Why should this change how you approach your work tomorrow morning?
It changes everything.
Because whether you are a developer, a researcher, or a strategist, your fundamental relationship with software is changing. For your entire career, you have been the doer. You have typed the commands, formulated the search queries, and manually connected the outputs of different programs. With the rise of agentic reasoning, you are transitioning into a manager.
That's the perfect word for it.
You will be overseeing a self-evolving collaborative team of digital experts. You define the overarching goal, you establish the parameters for success, and the multi-agent system figures out the how.
It is a transition from static prediction to interactive adaptive intelligence. This architecture democratizes incredibly complex problem solving, but it also demands a new skill set. We have to learn how to guide, evaluate, and ultimately trust systems that are operating with a degree of autonomy and internal logic that we have never had to manage before.
You become the visionary, and the agents become the engine executing that vision. But before we wrap up this deep dive, there is one final lingering thought inspired by these sources that we want to leave you with to ponder on your own.
Yes. As we continue to deploy these multi-agent systems into live, unconstrained environments, they're going to begin autonomously generating their own tasks to optimize their workflows. They will write their own novel tools from scratch, as we've seen with LATM.
Right.
Eventually, to reduce latency, they will likely develop their own unique, highly compressed communication protocols with other agents, entirely bypassing human natural language. The provocative question we are left with is this. At what point does their highly evolved collective reasoning become so mathematically advanced and so efficient that it becomes completely alien and untranslatable to the humans they were originally built to serve?
Now, there is a thought to keep you wondering exactly what your automated digital team is discussing while you sleep. Thank you for joining us on this deep dive. We hope it gave you a rigorous look at the architecture of tomorrow and a solid roadmap for where this technology is actually heading. Until next time, stay curious.